Perfect. So these are the contents we are going to talk about today. Um, this webinar is about modeling of reinforced concrete frame structures. And I'm going to show a very simple frame structure. So 4 columns, 4 beams. You will learn how to do frame modeling. We are going to use distributed plasticity. So you will learn how to create cross sections. And then we will talk about, in this first example, so everything will be continuous here. You will learn how to, what is a common problem in distributed plasticity, which is the dependency of strength softening material on the mesh size. So I'm going to show that when you refine the mesh, the response will be different. And so you will learn how to mitigate this problem by means of the fracture energy regularization. Then we'll start adding more details to the structure. You will learn how to add a nonlinear shear behavior using the section aggregator. And then we will show a common problem found with fiber cross-section and rigid diaphragm. When you combine them, you will see that beams will have a very large compressions, very large axial loads, while you do not expect them on beams. You expect axial loads to be almost zero. And then we will show you how to use the hinged beam compound element in STKO to create an axial release so that you can remove this problem. And finally, you will learn how to create nonlinear beam column joints. To model this one, you will learn how to create interactions, how to create rigid links, and how to create rigid zero-length elements to create springs for the beam column joint. Of course, now you have all the input file. This is the final structure that we will have. So the complete one: columns, beams, releases, rigid diaphragm, the node completely modeled. And now we are going to start to create this structure one by one. So let's create a new document. And let me move this one down here. Let me also clean. Of course, now I will give a brief summary of what we're going to see. But for example, these are the displacement, reaction force, displacement force curve of the plane frame model, the frame model refined after the regularization, which are basically the same. Then this green line is when we have the effect of the shear. So nonlinear shear will fail before the bending failure. Then we will see what happens when we apply axial releases. So you decrease the strength of the structure. And then finally, what happens when you create when you include the nonlinearity of the beam column joints. So let me start with a new file. Okay. So the first thing that you want to do is to go into the preprocessor, and you have a clean file like this one. Now a brief introduction. In STKO and in OpenSys, you don't have the concept of unit system. So before doing your model, choose the unit system you want to work and be consistent. Now in this model, we will use Newton and millimeters. So for example, when we start, you can set up the grid. Like in my case, I want the basic grid size to be 100 units, so 10 centimeters. And then you can start drawing. So you go on the geometry tab. Here is where you find all the tools for modeling. And the first thing that we want to do is to create the base nodes for creating the columns. So you click on the point, and every time you run a command in STKO, look at the terminal, because in the terminal, STKO will tell you what to do for this command. So in this case, for example, specify the first point by clicking on the graphic view, or you can type the coordinates, or you can press S to abort the command. Now, in this case, we want to create a 4x4 span structure. So let's place this one here. As you can see here, you can see the coordinates. So minus 2000, minus 2000. Then if you want to replicate a command, you either click here or you click the space bar, so you can repeat the command. And then let me place these other points here. Well, if you do a mistake like this one, Control Z, and of course you have the the undo and redo functionalities. And the last one here. Of course, you can move in 2D to be easier to do the modeling in 2D. Okay, back in 3D, we have the base vertices for the columns. We want to extrude them. So you have the extrude command. You click it, and it says, okay, select the geometries you want to extrude. In STKO, basically, there is just one extrude command that basically extrudes everything. So if you select vertices, they will be extruded into lines. If you select lines, they will be extruded into surfaces, and surfaces into solids. In this case, we select all the vertices, right-click, then you start moving, and you can see that the extrusion follows any direction. If you want to constrain in the orthogonal direction, of course, you have the orthogonal constraint, so you can just extrude in this direction. And now you can type 3000, and of course you see it here. So it will be extruded of 3000 units, 3 meters. And then you can keep on extruding it, or right-click and you stop, you finish the command. Now you have 4 columns and the previous 4 vertices that are still selected, so you can press cancel to remove them. So now you're left with just 4 edges. Now, of course, we have to create the beams. So go on lines. Now we don't need the orthogonal constraint anymore, but we need the OSNAP constraint. So we go near the previous points and we start drawing the lines for the beams. And then you click on the initial point, the polyline will be closed, and so the command is done. Now you have 5 entities. One entity is the entire polyline for the beams, and then the 4 columns. Now in this first example, we want to keep everything continuous, so we can join everything using the makewire command. Makewire is basically a command that joins these joint lines into a single polyline. So you click on makewire, and you select all the edges that you want to join, right-click, and now you have one single geometry. So all the vertices that previously were just coinciding, now they are physically one vertex. Okay. So now we have this geometry. This is not enough because we want to create also the rigid diaphragm up here. So what we need is to create a master node for the rigid diaphragm in the middle, and then an interaction for the diaphragm. So how can we create a node in the middle up here? You can just create a construction line from this middle point to this middle point using the OSNAP constraint. Then you go on points and you click in the middle here. Now you can get rid of this geometry here. So you select and cancel. Perfect. Now we have a wire here, which is our structure. And to make things clean, we can also rename it. So let's call it structure. And then, of course, you have a point here, which is the master node for the rigid diaphragm. So rename it and call it master node. Perfect. Now, the last thing that you need to do, we are done with geometries. Now we need to create some interactions because, well, an interaction is something that in STKO is used to connect these joint geometries. Like in this case, we want to connect the master node to the nodes of the columns. So you go on interaction, right-click, add interaction. By the way, every command can be run by the menu file or by the ribbon bar with the toolbars, like interaction, for example, here. Or you can run the command from the work tree, whatever you prefer. I personally prefer to work on the work tree. So let's add an interaction. We can give it a name, interaction rigid diaphragm. Then here you have an option, interaction type. 99% of the cases you want to leave the default one, which is node-to-node link. Basically, it means here you have a description. Basically, it means that this interaction will create 2 node links between the slave and the master node. There are a few cases in OpenCs in which you want to use these other 2 elements, but basically they are used by geotechnical engineers. So in our case, we are fine with this one. So let's press OK, and STKO says, okay, select the master geometries, and then press Enter to go to the next step of the command. So the master is this one. Then I press right-click or Enter, and then it says, okay, now select the slave geometries. And for me, the slaves should be these vertices. When I'm done, right-click, and here I have my interaction. Okay. So at this point, we are done with the geometry. Now we can go on with our modeling. The next step that we have is definition. So you may ask, what should I add in definition? Let's have a look. Add. In definition, you have under models, friction models or time series. Now in this example, we don't need any friction model, but we do need a time series. In particular, we just need a linear time series to apply the vertical load incrementally. So we are fine with the default one, just a simple linear ramp from time 0 to time 1 that increases the load from 0 to 1. And we can call it linear time series, and we can add it. Okay. Now, next step, when we're done with definitions, we have physical properties. Now, physical properties are basically all those OpenSys objects that are used to describe the constitutive behavior of your structure. So, material models and cross sections. Now, let's move to the property tab so that we can see the section extrusion here. Now, in this example, we want to create fiber cross sections. So the first thing that we need to do to create a fiber cross section is to create uniaxial models. So let's go here under physical property, right click, add, and we are going to add a concrete. So let's go under model, material, uniaxial, and concrete materials. And for this example, we will use concrete 01. Let me put some values here. So minus 35 megapascals, minus 0.002. Minus 5 of residual strength. And here we can put, just to start, 0.015. Let's say this is our ultimate strain, okay? And we're going to see, then you will see how I will change this one when we will refine the mesh. So let's see how this parameter works. So whenever you create a material model in STKO and you are not sure about the material parameters, you can use the material tester. In the material tester, basically, you are going to choose one strain protocol, and you're going to apply it to this material, and you will see what is the stress response. So here we choose a cyclic increasing behavior. We choose, let's say, 100 subdivision for each cycle. The target strains should be similar to the peak strain in this case. We don't want to test it in tension, as this material doesn't have any tension, so only in compression. And let's do a test. So this is how my material behavior, this is the response of the material with these parameters. So for me it's fine, so let's click OK. And we can create now the same way, the steel material. Steel, materials, uniaxial, steel and reinforcing steel, steel 02, to create a Menegotto Pinto material model. And for this one, we choose 487 megapascals. And here we have some values that describe the shape of the cyclic, the distr curve. So 18.5, 0.925, 0.15, and 0. Here we don't need any hardening. And the Young modulus is 206,000. Yes. Once again, let's do a test just to make sure everything is correct. And okay, this is my material model. Perfect. Now the third step is to create the fiber cross section. Now in STKO you have two ways to create a cross section. So let's go here, add. Let's give it a name. So we will start with the column fiber section. So we go under model. This time we need to go under sections. And here you can see fiber or rectangular fiber section. Now fiber is the most general way of creating a fiber section, but you need to draw it by hand. So for example, you click here, and you have another small cut here where you can draw your fiber cross section. Now this is fine for general shape cross sections, but when you have to do rectangular fiber section, this one is very time consuming. So we have another facility here, which is section, rectangular fiber section, which basically is the same but optimized for rectangular shapes. Okay. So here you can choose. The first optional parameter is the GJ, which basically is the shear modulus times the torsion constant, and in this case is 4.2 E13. We are going to work in 3D, and the size of my cross section will be 500 millimeters times 300, and you can see here the drawing that updates accordingly. 20 millimeters of cover, and then these one are fine. We need 3 rebars at the bottom, 3 rebars at the top, and then 2 rebars on the left and right side. Okay. So next step is to assign a material models. Okay. So we can start with the rebar material, which is the steel one. And now, as you can see, these fibers are colored with the same shader, the same color given to the material model. And then you can choose the concrete material for both for the cover and for the core. Now let's see what happens if I only choose the concrete for the cover. Click here, and then you see something here that happened. I didn't choose any material for the core, only for the cover. So STKO understands that you define an unconfined material model, but you want STKO to automatically compute the confined material model. And STKO will compute this one according to some formulations here, and the geometry of this cross section and these stirrups. Now, of course, for example, if we change the stirrup diameter to 8 millimeters, you will see that the confined concrete decreases. If we increase the spacing in the same way, it will decrease a little bit. And then we change the number of legs to 2 and 2 also in the other direction. And this one will be updated accordingly. Now, if you don't want to use these automatic calculation of confinement, of course, you can select your own constitutive model and say, okay, don't do your calculation. I don't want to compute the confined concrete, or I have my own confined concrete and you will put it here. But if you leave it as known, STKO will compute it for you. Now, in this case, we want the computation of the confinement, so we are fine with this one. And let's press OK. So now we have the column fiber. We still cannot assign it to the columns because we need an extra step. We have the materials, we have the cross section, but we need the integration scheme for the beams. Because probably, as you know, in OpenCs you have many choices for the integration scheme. So how do you do that? You go on physical properties, you select add, let's call it column property. You go under model, special purpose, this time beam column, and you can choose beam section property. Then you have the old one, which is the old version used by OpenCs, but keep things updated and use the new one. But in the new one, basically, you first can choose the kind of integration scheme that you have in OpenCs. So the standard integration type, then you have the user-defined, the hinges, and so on. Many of those are not even documented in the OpenCs wiki. In this example, we are fine with the standard integration type. And for the standard integration type, we have many sub-integration schemes. And we just want the Lobato one. So let's say the standard one that you can find in any other software. You can choose the number of integration point. We are fine with the default of 5 integration point, and we choose the fiber cross-section. Now, by doing this, our cross-section will just have the P, M, My, Mz behavior, and of course the torsion, because the torsion has been given in the cross-section through the GJ parameter. Okay, so in this case, we don't have any response in shear, at least in the cross-section. So we press OK. Now that we have this one, we can assign it to the geometry. Now the problem is that if I select the geometry like this, and I drag and drop the material model, I will assign this material model to this property to the entire geometry. And this geometry is made of several edges and several vertices. But now, actually, I want to assign this one only to the column. So how do I do this? Now, let's press Ctrl-Z to undo the assignment. If you look here, you have several buttons here that are used to handle the selection. Now, you can see what they mean in our documentation. But in this case, we just need to focus on this one. This one say, okay, I want to select the entire geometry. If I switch it off, I can select the sub-geometries like this. Okay? So now in this case, I'm able to select just the columns. like in this case. Once I have all the columns, I simply drag and drop the property for the column. Okay. Okay, now let's do the same for the beams. Now for the beams, we'll use the same cross section with just one small modification. So instead of creating a new one, I can right click and click clone. So I can edit it and just do the change that I want. And in this case, we can call it beam fiber. This one will basically be the same. We are just going to change the rebar layout. So we're going to use 2 rebars on the bottom, 2 rebars on the top, and no rebars on the left and right sides. And one more thing, since this is a beam, we don't need the computation of the confinement, so we can directly choose our unconfined concrete here. Okay, so these are the only modifications that we need for the beam, and we press OK. Now, in the same way, we can clone this one, the column property. We can clone it, edit it, and we call it beam property. We leave everything as it was before. We just changed the section tag. It was column fiber, now it is beam fiber. Right click OK. And now we can select all the beams. As you can see, I still have this button switched off, so I can select only the beams. And I drag and drop this one, beam property. Okay. Now, as you can see here, you have all colors that are basically chosen randomly by STKO. If you want to change some of those colors, now in this case, for example, I want to make it a little bit more transparent, so we can see inside. So you can go here, edit shader. You can choose whatever you want. Now in this case, I just want to lower the transparency so that we can look inside. Okay, and let me do the same for the beams. Okay, let me lower the transparency. Okay, perfect. Now we can look inside. Perfect. Now we have the geometry, we define that time series, and all the physical properties. But let's say what happens, for example, if I want to, I'm fine with the orientation of the beams, but actually I would like the columns to have the strong direction along the global X direction. So how do I do this? You know that in OpenSys you can do it with the coordinate transformation, but how does it work in STKO? Well, if you click on this button here, you can show hide the local axis. By default, they are hidden. Now let's show them. And here you can see the default local axis assigned by STKO. And in this case, for example, you have the strong axis, which is the y-axis, oriented along the global y-axis. Now we would like to rotate them. Now, of course, you can rotate the cross-section from here, but this is not the most efficient way. We have a tool for that, which is called local axis. Now let's go here, add, and we can call it column orientation. Here you can choose between rectangular, cylindrical, or spherical local axis. Now in this case, we just need rectangular local axis. We click OK, and you can follow the instructions here. So select the first point. The first point, it is not important for the rectangular, while it is important for the cylindrical and spherical. Now the first point here, and then since we want the y-axis of the column to point along the x-axis, we just need to rotate this one, and let's click here, and then a third point to define the plane. Like in this case, it is fine to pick just a simple point in this direction. Perfect. Now we can simply select all the entities that should have this new local axis. And like for the material model, we simply drag and drop it. Now you can see that they changed the orientation of the cross-section, and of course they changed the direction of these arrows. Now the y local axis is pointing according to this local axis. Okay. So basically at this point you know how to create a geometry, how to create interaction, how to assign physical properties, and how to orient beam sections, which is very much important. Okay, now we can save it. Let's give it a name. Let me call this one example 02. And let's call it model. Now we are done with physical properties. We can switch off the orientations. We don't need it anymore. Now we need to define, the next step is to define element properties. Now, while the physical properties were defining the constitutive behavior of elements, the element property will define the finite element formulation, and so the kinematic behavior of the structural elements. Now, in this case, we just need one single element for all the geometries, so both for beams and for columns. Let's call it beam element. And for all of them, we want a beam column element and a force beam column. Okay, we are in 3D, linear kinematics, otherwise we can choose P delta or rotational. We don't want to assign any mass, we don't need any of these optional features, so we just press OK. And we select all the edges. Now, how you can select all the edges? You can simply go here, but you can do it manually, of course, or you can go like this one. You expand the node of the structure, you select all the edges, and click select. And then you can drag and drop the beam element. Fine, so now you have physical properties and element properties. Now the next step is to create boundary conditions. Let's go to the boundary condition tab, so we don't see the extrusion anymore, but we will see the representation of the boundary conditions. So the first thing that we want to do is to create a boundary condition to fix the base of the structure. So right click on condition, add, and we call it fix base. We go under model, we need a constraint, and we need a single point constraint, the fix one. And then here we have to tell STKO that we are working in 3D and with 6 degrees of freedom, so displacement plus rotation. So we have all the dots here, and we want to fix them all. So just check all those checkboxes. And now, as you can see here, after you choose the model, you need to select the entities this condition will act on before pressing OK. So we want to apply these on all the base vertices, like this, and press OK. Okay, now you can see, of course, the representation of the condition. Let's say for some reason you made a wrong selection. You want to include an extra node, for example. You can go here, edit. As you can see now, it goes back to the previous selection, and you just add one item, for example. You press OK, and now this condition is working also in this point. Now I go with an undo, because of course I don't want to do that. So if you go on edit, you can see now you have only these points. And press OK. Perfect. So now the fixed boundary condition is only at the bottom. The next step is to create a fixity also for the master node here. As you may know, here we are going to create a rigid diaphragm, but a rigid diaphragm will only connect 3 degrees of freedom of the master node to the slave nodes, which is the in-plane displacement and the out-of-plane rotation. But the other 3 degrees of freedom are free, so we need to fix them. So let's call this one fix master. We go under model, constraints, single point constraint fix, once again in 3D, 6 degrees of freedom. And we want to fix the out-of-plane displacement and the out-of-plane rotations. And we click this one, select this one, and press OK. So we also have this boundary condition now. Then we need the boundary condition for the rigid diaphragm. Let me move this one down here. Okay, so condition, add, we call it rigid diaphragm. We go under model, constraint. This time a rigid diaphragm is in multi-point constraint, and we choose the rigid diaphragm. Here you can see the perpendicular direction. Following the documentation, it says, okay, if my plane corresponds to the XY plane, I need to select the third direction as the normal of the plane. So once I choose this one, I need to select the entities this condition will act on. In this case, this condition will act on the this interaction. So you select it and press OK. And as you can see now, the representation of this boundary condition is on the interaction for the rigid diaphragm. Perfect. Now we need 2 extra boundary conditions. In this case, loads. We need vertical loads, and we want to simulate the vertical load of the structure using loads and element loads. We can use the beam uniform distributed load. We are in 3D, and we want to apply the load in the z direction, because if you switch on the representation of the local axis, the z local direction is the vertical one. So it's this one that we want, and we apply minus 5 kilonewtons per meter or minus 5 newton per millimeters, and we select all the beams, and we press OK. So now we have the distributed load on the horizontal lines. And then we need one last load, which is a nodal load of a unit force in the master node that we will use for the displacement control analysis. So right click on condition, add horizontal load. We go under model, loads, force, and this time we need a node force. A node force, and we want to apply it in the x direction. We just use one. Actually, we can use any number, but if we choose one, then when we are going to visualize the load multiplier, which in OpenSys is the pseudo-time step of the displacement control analysis, it will be exactly equal to the opposite of the base reaction. So it's easier to visualize the results if you choose one. So OK, and I select the node this condition will act on, which is this one. And here you can see the unit force. So now we are done also with the definition of the boundary conditions. So we can save this file now. And then we can start adding all the analysis steps. So the first one will be, as usual, the recorder. We go under model, recorders, and PCO recorder. Now the first thing that you have to do is to choose a name. We can call it results. And then you choose everything you want to record. For example, in the nodes, we just want to record displacement and rotations, and reaction force and reaction moments. And then at the element level, we want to record section forces and deformation on the Gauss points to visualize the internal stresses of the beam. And then we also want section fiber stress and section fiber strain. Now, actually, we don't need material stress and material strain, but since we will need it later on when we will add the rotational springs, let's check them right now so we don't have to change it later. Okay? Now, the second step will be to add all the boundary conditions that should be applied from the very beginning. So add boundary conditions. We go under model. Boundary conditions, so constraints and loads should be applied using patterns. A pattern can be added or can be removed. Now in this case, we want to add a pattern. And since we want to apply the constraints, we need to choose constraint pattern. Here you see two vectors, the single point vectors and the multi-point vectors. Now we have two single point constraint, fix and fix master. So we make room for two entities, and we choose the fix base and the fix master. And we press OK. And we have just one multi-point constraint, which is the rigid diaphragm. So we go here, we create room for just one, and we select the rigid diaphragm. And press OK. Okay, now at this point, we also have the first three boundary conditions applied. Now we want to apply the vertical load. So we do something similar. So add vertical load. We go under model, pattern, add pattern, this time a load pattern. Now for the load pattern, we need to choose the time series. We have the linear time series that we created at the beginning of this presentation. And now we have the vertical load is actually an L load. So we need to apply this load in this vector here, the second one. So click here, edit. We make room for just one entity, and we choose the vertical loads. Okay. And OK. Now we are ready to run the first analysis. So once again, analysis step, add. We can call it this gravity analysis. We go under model and we choose analysis, analysis command. Here you have all the tools we need for the analysis. Now in this case, we choose a static analysis. Now for the constraint handler, in this case, we cannot use the plane constraint because of the rigid diaphragm. The plane constraint cannot be used with this kind of multi-point constraints. We can use any of the other three, but I prefer the penalty one because now it is very simple, the model, but then we will start adding many other constraints. So when the constraint system becomes very complicated, probably it's easier to use the penalty method. I'm not going to talk about this one probably in a future webinar, but for the moment, let's choose this one. And in this case, you need to choose a proper penalty parameter. Now, typically the default is fine. Now, in this model, it is better to use 1 to the minus 16 because of this one should be computed as the largest stiffness you expect on a node. You take the order of magnitude, for example, in this case, it was 8, and then you add 8 to this number, and thus I have 1 to the power 16. Then for the number, we choose the default. For the system, we choose the default is fine. Now, at this point, the Newton method is fine, but then we will start adding many other nonlinearities. So the Newton with line search will work better. Perfect. Now, for the test command, whenever you choose the penalty, like in this case, you can never choose any norm of the unbalance. So you can only choose something which is the norm of displacement increment or the relative norm displacement increment, but nothing that has to do with the unbalance, because the penalty leaves the unbalance with a large force, so it will be very difficult to bring it to 0. So in this case, we choose norm displacement increment, and we choose a tolerance of 1 to the minus 4. Let's choose 100 iterations, and we want to see the convergence of our problem. So we check on the print flag, and we set the print flag to 1. 1 means show me the norm and the number of iterations. Then the integrator. In the first analysis, we want to use a load control for the test analysis, and we are fine with using 10 steps. Since we want to use 10 steps, we set the lambda to 0.1. So at the end of these 10 steps, the total lambda will be 1. So the 100% of the vertical analysis. Then after this, we want to check the load const command. This command basically says all the element loads or all the nodal loads applied before this analysis will be kept constant during the following analysis steps. And now we are free to reset time step to 0, because at this point, all the previous loads will remain constant despite of the value that we assign to the pseudo time step. Okay, so we are fine with the vertical analysis. Now we can add the horizontal load, and finally we can do the horizontal analysis. So let's go here, add horizontal load. We go under model, pattern, add pattern, load pattern. Here we can choose a time series, even if it is not important, because this one will be displacement control. So actually the time series here is just a placeholder, will never be used. Now the horizontal load, as you can see here, is a force, node force. So we need to apply it on the load vector, not on the LL load. So we go here, we create space from one item, and we choose the horizontal load. We press OK, and we are fine. Now we need to run the horizontal analysis. Since it will be very similar to this one, let's clone it. And we can now edit it to make some minor changes. And we call it horizontal analysis. It is still a static analysis. Penalty method is fine. Newton will end search. Here we're going to have some nonlinearity, so I want to decrease the tolerance just to 1 to the minus 3. Number of iterations is fine. But here we need to create a displacement control. Now you go to displacement control, you see here selection set. We need a selection set that contains the vertex, the node, that should be controlled. Actually, we forgot to create a selection set, so leave this one to 0 for the moment. Then we will go back here, create a selection set, and we will come back here. In any case, we want to fix the first degree of freedom, which is the displacement in x direction. And we want to apply an increment of 0.1 millimeter for 1,000 steps, so to reach 10 centimeters. Now we don't need the load const, because this one will be the last step of the analysis. So let's press OK for a while. Now we need to create a selection set for the load control, for the load, the control node, sorry. So we go on selection set, right click, add. Now we need to select the control node, which is this one. right click, and we give it a name, control node. And now here you can see you have a new selection set. Selection set are used just to recall a previous selection, like this one, or can be used in commands that require a selection set, like the displacement command, the displacement control command, like in this case. So here we say that the control node is identified by this selection set, and we press OK. Okay, now we are fine, we can save it. Now we did everything. The last thing that we need to do is the mesh. As you can see in STKO, you do all the modeling in the CAD geometry, and then at the end you do the mesh. Now in this case, we can assign a seed. The seed is basically the how large should be the finite element. Now in this case, we are fine with just one element per geometry. Okay, so we start with this one, assign, done, and we build the mesh. Now, as you can see here, you don't have any intermediate point because we don't want it. Now we're fine to run the analysis. So let's run it. It will take a few seconds. Okay. Now we can go to the post-processor. Let me save first this one. Okay. Let's go to the post-processor. And now we can load the output database. So we are working on the example 02 folder. And here are the results. So we click on it. And here we have our database loaded. And by default, STKO creates a new plot group with a deformed shape plot. This is a default. Of course, you can remove it. And you can do some different plot. Like, for example, in this case, I want to see what's going on the fibers. So I can choose the shell fiber section plot. And I want to see what's going on in terms of, for example, if you want to see the stresses, you can switch off, I don't know, the steel, for example. Actually, this model is the confined concrete. So in this case, I switched off the confined concrete. You can switch off the steel, so you can see the stresses only on the unconfined concrete. In this case, you can see the stress on both the unconfined concrete and concrete. Or you can switch them off and visualize the stress only on the rebars. Okay? Or in this case, we want to see actually not the stress, but we want to see the strain, because in this case, it's easier to see where is the formation of the plastic hinge. Now let's give a larger deformation so that we can see what's going on. And here you can play with an animation. You can move the slider on and on. So as you can see at the beginning, the strain is quite smooth. So you have a larger strain here, and then it gradually goes to 0 here, and then tensile is in tension on the other side, as you expect. And then when you push it even more, you have localization on just the base integration point, meaning that here you have a formation of a plastic hinge. Okay. So here is how you can expect results from a visual point of view. Now let's say we want to export the load displacement diagram in this case. Now let me go here. Let me switch off the nodes, switch on the nodes so I can see them, because I want to select the master node and export the displacement versus load multiplier curve for this node, so the pushover curve. How do you do this? You go on chart data, you click on chart data, and here you have to choose. In this case, I want to extract a result on nodes, so I click on this one, then I press next. I want to extract the results only for the second stage, which is the pushover analysis. I don't care about the vertical one, so I click here. And I want to export in the Y data, the displacement in the X direction versus the pseudo time step, because in the displacement control analysis, the pseudo time step is actually the load multiplier. So you press next, and it says, okay, perform your selection. I want to select this one. Okay, we have a question. Just a second. Okay, thank you. Okay, so I select this one, next, and let me call it UF basic, finish. And here you have the displacement versus load multiplier. Now the load multiplier here is in the x direction, but it is the same. So you see initial linear elastic behavior, then a short hardening, and then you have a peak here, and then the softening. Okay. So the typical behavior that you would expect. Now, if we go back in the preprocessor and we change the mesh, now let me do something. Let me go here. Here you can see you have a checkbox that says linked to the database. This means that this data set will be linked to the database. So every time I change the analysis and I reload the data set, this one will be updated accordingly. Now, since I don't want to do this, because I want to compare this response with the new one, I go here and I uncheck it. Okay. So let's go back to the preprocessor, and I just want to change the mesh. So the model will remain the same. I just need to change the mesh. I want to make it finer. So I select uniform by division, and I select 3 elements per geometry. Click assign, so you have a preview of the subdivisions, and you say you click done, and then you build the mesh. Okay, now you have 3 elements for every member. Now we can save it and run the analysis again. Now, as you can see here, we will have convergence problem, because you will see that the response of our structure, now that the mesh is finer, will be much more brittle. And let's see why this happens. As you can see here, at a certain point, it cannot invert the flexibility of the force base beam column. And let's wait a little bit and it will stop the analysis. Okay, we can actually stop it, we don't care. Okay, perfect. Now we go back to the post-processor, we reload it. Okay, now we can go just here, we change. Okay, let's see what's going on. When it is starting localizing, let me go back to the strain other than the stress. There is a convergence problem. So let's go here and plot the same load displacement curve on this discretized model, and let's see what happens. You actually would expect to obtain the same result, but you're not going to obtain the same result. So once again, on the second time step, x displacement versus load time step. Next, this is our node. Next, you have refined. We don't need to create a chart because we are going to put it in on top of the previous chart. So let's finish. This is our response. We go here and we add it. So the refined one. Now, as you can see, the refined one, apart from the fact that we have convergent problem, but we reach almost the same peak, and then it drops suddenly. It doesn't follow the previous load displacement curve. Even if we didn't change anything, we just changed the dimension of the mesh. This happens for a problem called strain localization, which is this one basically, which is related to the fact that you're using a material model with strain softening, but with a continuum model, which is the beam element, for example. Now, I'm not going to explain the theory of this one, but basically, whenever you have softening, the fracture energy, which is the area underneath the stress strain curve, should be related to the size of the finite element. Now, in this case, we made the finite element 3 times smaller, so we need to increase the fracture energy of 3 times. Now, here you have a formula, and on the file that you are going to download, there is also an Excel file where you can compute this. And basically, this Excel file, following this formula, changes the ultimate strain in such a way that the total fracture energy is equal to the previous fracture energy times a scale factor, which is related to the length of the finite element. And in this case, to make it 3 times larger fracture energy, I need to increase the ultimate displacement using that formula. In this case, is 0.04287. So let me go back here and let me change the ultimate strain, which is minus 0.042. Let me see the value. 42857. Okay. Now let's save it. and rerun the analysis. And now we should obtain more or less the same results as the original mesh. Let's wait a few seconds. As you can see here, we are having not the same, as you can see now we converged. We didn't have the same convergence problem as before. So let's go back here. Now as you can see, I left this one linked. So now I go here and I just update or reload the database. Let's go back here. And as you can see now, it updated the previous curve and they are pretty much coinciding. Of course, there is some difference because the regularization is not a very precise formulation, but as you can see, the response now are coincident, basically. So now you have learned how to do what is a common problem in distributed plasticity, which is this kind of dependency of the strain softening response to the mesh size. Now, the second point of our presentation will be to add shear behavior. Now, up to now, we just have the PMY, the PMY-MZ interaction plus the torsion. We don't have any response in shear, at least on the sectional level. Now we want to add non-linearity at the sectional level in terms of shear. So how can we do this? Well, first of all, you can use any formulation. In this case, we are using Cezanne and Moelle to compute the shear strength, but you can use any other formulation. But how can we do this in STKO and OpenSys? So let's go back to the previous example. Let me save it. And now let me save it with another name. So we have different files. And we call it model with shear. Okay. So to create the shear, I first need to create two uniaxial behaviors, two uniaxial material to describe the shear in the X, in the Y and Z direction of the columns. So let's go to the physical property and click add. Now let me go this one shear in the Z direction, which is the width direction. In this case, it is this direction of the column. And for the shear, we want to choose, well, you can choose any uniaxial material behavior. In this case, we want to choose the modified Ibarra Medina-Krabinter with pinching. Let me put some values here. I have them drawn here. So 5.01 to the power of 9. And then we have 0.00197. And the same for the negative, 0.00197. Then the total shear strength will be 1.8 thousand. The same one with the opposite sign in compression. Then we have some values describing the cyclic behavior. And we go quite fast here. Then all this value to 0 to 1. And then the ultimate, in this case, it is theta and moment, because this model was made for moment rotation, but in this case we are using it for shear and shear deformation. So the plastic shear deformation will be 0.001, same for the negative side, and the residual 0.1 and 0.1, and the last one will be 1 and 1 because we just don't want to. This is the residual one also. 0.1, 0.1, and here we need to put 1 and 1. Simply because we don't want to drop the shear to 0, never. Okay, so we are fine. Let's see how does it look like. So let's test it in a cyclic behavior. Let's push it a little bit. Okay, so this is how our shear behavior looks like. So it is fine for us. And now we are going to create the second one for the Y direction. That is this direction, which is the strong one. Go back to property just to recall the, the orientation of the beam. Now we can just clone it because it will change just a little. So we edit it. And we choose shear Y, which is the strong direction. And in this case, we just change these values, 0.00342 0.00342. And then we have here the strength, which is 326,000 and minus 326,000. All the others are basically the same because of normalized values. Let's check it. Okay, perfect. So now we have the two uniaxial lows for the shear. Now, how do we put this inside the beam property? Well, first let's move them upward because we need to place them just before the column property. So once again, and here, and the same for the other direction. Okay. Now we need to create something called section aggregator. Basically, in OpenCs, you can combine the behavior of a fiber section with other independent behavior in shear using the so-called section aggregator. So let's call this one column section aggregator. We go under section and we choose the aggregator. Now in this case, you can either choose every component independently, or you can choose for P, MZ, and MY the cross section, like in this case. You want to use a cross section, which is the column fiber section. Then we don't need to put any torsion because the torsion was already defined in the cross section using the GJ parameter. So we just need to choose something for VY and VZ. So for VY, we choose the shear in the strong direction, and here we choose the shear in the weak direction. And we are fine. Now we move this one upwards just before the column property, so that now we can go here in the column property, which is the actual property assigned to these elements. Right click, edit, and now we can just change this column fiber to the column section aggregator to include the shear deformation also. So we just press OK, and we are done. Basically, now your model has the shear behavior with fully nonlinearity in shear. So let me save it. Let's run the analysis and let's see if something changes. Now, what is going to happen? The shear, depending on the shear strength of this column, the response can be the same as before, meaning that the bending failure comes before the shear failure. Or you can see a different response, meaning that the shear failure happened before the bending one. So let's see what's going on now. Okay, the analysis is finished. Before reloading it, let me unlink it so I don't reload this one. Now let me reload the database. Okay, so let's go back to, now you see two different results for the shear, for the fibers, because now you have different components. The columns are different from the beams now. Okay, so these are the two previous curves. Now we're going to extract once again the curve, the load displacement curve. So let's go to chart data, extract chart data on nodes, stage number 2, displacement versus pseudo time step. Next, and we call this one UF with shear in the strong direction. Let's call it in the strong direction. And just shear, it's the same. And we don't want to create a chart because we're going to superimpose it on this one. Now let's click add and select this one. Okay. Now you see that basically this one is perfectly the same as the previous one. So this means that basically the shear strength of this column was sufficiently high so that the bending failure came before. So actually the response is exactly the same of what happened before. Now let's see what happens, for example, instead if I change in the section aggregator, I swap these two values. So here I put the weak material, and here I put the strong one. So let me put the weak direction in the other side, and the strong one here. So now the y direction, which is the one in which I'm pushing, will have the a smaller shear strength. So let's press OK and run the analysis. Let's wait a few seconds. So now you can see you're starting having some convergence problem. That was basically the shear failure, as you will see now in the output. Okay, let's press OK. Go back to the post-processor. Now this one is linked. So as soon as I reload this one, the green line in the chart will change. And as you can see now, the shear behavior happened before the pending one. So now you can see the difference, okay? And now here, now you know how to add a nonlinear shear response to a distributed plasticity model. Okay, now let me unlink this one, because we're going to add something new now on this model. Let's go back. Let me save this one, and I want to save it with another name. I can save this like a model, shear, and action release. Why am I talking about action release? Now let's go back to the post-processor, and I want to show you something that happens with when you combine fiber cross-section for beams and the rigid diaphragm. So to see that, let's create another plot group, and we are going to use a Gauss point plot because we want to see the axial stress, the axial force at every Gauss point of the columns. Now in this Gauss plot, I'm going to choose section force. This one is for the columns, and this one is for the beams. So let's choose the one for the beams. As you can see here, the axial stress is very high. Now let's see how this axial stress evolves during the analysis. So we're going to choose just one of them because, by the way, it is constant almost. So chart data, extract. This time I want to extract something on the Gauss points. So I click on Gauss point, click on next. Here I want to extract something from all the stages. So the static one and the pushover one. And now I want to extract the section force. I'm fine, yes, with the axial force against the time step ID. Okay. So we will see how the axial stress in the columns evolve during the analysis. Let's call it axial no release. So without the release, let me create a chart for this one instead. Finish. Now as you can see, we are working in Newton. So you start the analysis with almost zero normal stress here, axial stress. And then as you go into the nonlinear behavior, following the hardening part, you even reach 1000 kilonewton, which is something that you do not expect on this kind of beams. Actually, this one is much more than the total vertical load that you have on columns here. And then only when you have some softening, you start having a decrease of the axial stress. Now, why is this happening? This happens because when a fiber cross-section, you know very well, when it goes into the nonlinear range, the neutral axis shifts, in this case, towards the top. And so at the level of the center line, you should have a positive strain. Unfortunately, the rigid diaphragm does not allow the beam to enlarge in the axial direction. And so the beam will generate these, as a reaction, will generate these very large axial stress inside. So how can we solve this one? Because actually, this very large axial stress can change the behavior, the results of your structure here. And we are going to see. Now, our objective would be to release the axial stress, the axial deformation of the beam, so that the beams can just slide over the columns, but the columns are still affected by the rigid diaphragm constraint, okay? So how can we do this? Let's go back to the preprocessor. Oh, and just not to overlap not to cancel this plot, I want to uncheck it. I want to unlink it. So let's make sure that everything is unlinked, okay? So we can do a comparison. So here we have the model with the axial release. Now in this model, in this case, you will see how to create a release at the end of the beams and how to use the beam with hinges, the hinged beam element that we have in STKO, which is actually a compound element. So it's not a new element. It's just a standard regular element that you have in OpenSys. But while you draw them attached like this one, STKO will generate internal nodes and some springs on the two sides, okay? So it will be very easy for you to draw this kind of structures. So the first thing that we need to do to create this model is to create first a stiff material, a very stiff axial material that will be used to represent the continuum behavior between some degrees of freedom, and you will see why. So let me create a very stiff material. Let's choose uniaxial, some standard uniaxial materials, and we choose the elastic. Now this value should not be very large. In this case, 1 to the power of 15 is fine. Okay, and here we have our stiff material. Then we need a zero length material to be used in the hinged beam, and you will see why. So we create a zero length for the continuum part. Continuum. So basically, one side of the beams will be in continuity, while the other side will be released only on the axial direction. So we need a zero length for the continuum side. Let's call it zero length for the end of the beam, or for the start of the beam, the start node of the beam. Okay, and we are going to make this one continuous. So go to zero length material, zero length. We choose 3D and 6 degrees of freedom, and we want to fix all of them in continuity. So we check them all the degrees of freedom, and we choose stiff for every one. Stiff, stiff, stiff. Okay. Now we clone it, and we do the same for the end node of the beam. So clone, edit, and we call it zero length end. Basically, it will be the same except from the axial direction. We uncheck it, so the axial direction will be released in this way, while it will be continuous in all the other degrees of freedom. So we press OK. Now that we have all of them, we can just create, let me go here, add an hinged beam property. So the hinged beam property will basically be a special purpose hinged beam physical property. Now this one basically is asking you the physical property for the inner beam, which in this case will be the same that we used before, so the beam property. Okay, so with the fiber cross section. And then it is asking me for the I and J zero length. So what should be the hinges at the two sides? Now the I side, it will be the starting one, so the continuum one. And on the other side, we will have the end one with the axial release. Okay. So keep in mind to put the release only on one side. So let's put OK. Now that we have this one, we can assign it to the beams. But let's first do a check. Let me show the local axis. We have to make sure that all the beams are pointing in the same direction. Okay. As you can see here, these one are going down, these one are going upward, this one are going on the right side, and this one on the left side. In this case, it is not important, but when we apply the end releases, we want to apply the releases on the same side. So in this case, I'm going to reverse the direction of this one. So it will be according to the direction of this one and the direction of this one. Okay, right click. And so now you can see these and this one are going both on the positive x-axis, and now this one and this one both along the positive y-axis. Okay, now that they are pointing on the same direction, I can switch off this, go back to property, and I select all the beams. So 3 and 4, and I drag and drop this different material model. Okay, now as you can see, as a representation for the hinged beam, we have a small gap here. It is just for representation, okay? Now we need also to change the element, because before we assigned the same element, the first base beam column element, to everything. Now we need to change the element of these beams. So let's go here. Let's add an hinged beam element. And we choose it from model, special purpose hinged beam. in here we have to choose the beam element for the central element, and then the zero length element. But unfortunately, we didn't define any zero length. So let's press cancel for a while. Go back here. Let's add a zero length element. This is pretty straightforward. We go to zero length, which is zero length. We just need to specify that we are in 3D, nothing else. Okay. And now we can just go here, add hinged beam element. Special purpose hinged beam, and we want the same beam that we had before for the inner element, and then we want the zero length element for the 2 hinges. So we press OK, and now we need to assign it to the 4 beams. Drag and drop this element here. Okay, now we can save it. We can just run the analysis again to see the difference. So what's going on if we release the axial stress so that the rigid diaphragm that does not apply all those very large axial stresses on the beams. Okay, we're done. Back to the post-processor. I will reload this one. Okay, so as you can see now, the axial stress, as you can see from here, it's very small. So let's first select this one as before, and let me ask again for the Gauss point result, all the stages, and section force P against the time step ID. So next, axial no release. We don't need to, but let me create a chart first. Okay, as you can see, it is very small. It reaches only a peak of 3 here when we have some convergence problem, and then almost 0. Now let me remove this one, and I want to add it on top of the previous one. As you can see, it is 0 here. So basically, we remove this problem. Before there was this very high axial stress, now it is 0. And graphically, what is going on? So let me create another plot group with a surface color map. Here it is easier to visualize. I switch on the nodes and I switch off the beam exclusion, okay? Let me place displacement deformation scale of 2. Now, as you can see here, the node of the beam is just sliding to allow the beam to develop axial deformation, and so to be in equilibrium with the 0 axial stress outside. Here it is what's going on, okay? So this is one way to get rid of the problem. Otherwise, you can just draw your slab, so you will consider the actual the real axial stress, the stiffness of the slab. Okay, so now I'm going to release to unlink this one, and also okay. Yes, something that we need to do now is actually to extract the load displacement curve so that we can compare it with the previous one. So this was the response with shear, but with the effect of the rigid diaphragm. Now let's see what changed. Now we need to extract something on nodes, only on the second stage. And we want to extract displacement along the x direction versus the load multiplier. Next. And we call it U with release. UF with release. Finish. Okay, let me remove this one as I'm going to add it here. Add UF with release. And you can see it here. You have a smaller stiffness now, and the smaller strength, because here, of course, the strength was higher due to the axial compression, larger ductility, okay? And finally, we have, let's say, in another 15 minutes, I'm going to show you how to add the last nonlinearity that we want to include in this model, which is the nonlinear beam column joint, okay? Now the joint is completely continuous. So now we're going to add also this nonlinearity and see what will happen here. So let me unlink this one, okay? Let's save it. And let me save it as another name. I can call it model, shear, release, and joint. Okay. Now the joint, as you will see here, will be drawn manually, and it will be quite time consuming. But in fact, we are working now on a procedure to create these beam column joints automatically. Now in this case, I'm going to show you how to do it manually. So back to the geometry. What we need to do now is to detach all these beams and this column from this node. Then we will duplicate this node to create the scissor model for the joint. So how can we do this? Well, the first thing that we need to do is to create 4 support points here. Once again, here, here, and here. So we have 4 points that we are going to use to copy and cut the other lines. Okay. So first of all, let me select all of them. So let me go back to the entire geometry selection. So I can select only these nodes. And I want to copy them downside to create the rigid offset for the column. So let me copy them. The beam has a total height of 300, so I'm going to write here 150. Okay, so these ones will be used to cut the column. Then I'm going to select this one and this one, and I'm going to copy it on this direction. Now in this direction, the column is 500, so 250. Okay, and now I'm going to mirror them for the other side. So let me select these two, click mirror. I want to create a copy, of course, from here to here. As you can see, this one is the mirror plane. Okay, perfect. Now I do the same in this other direction. So first I select the 4 support nodes. I copy them. In this direction, instead, the column is 300, so 150. And once again, I mirror them. So let me select this one, then press mirror from here to here, and OK. Perfect. Now we have all these other points. Now we need to use them to cut the structure. Okay, so I'm going to select all these points without the corner ones. Okay, only these ones, these extra nodes for the cut. And also this one. And then I also select the entire structure and I click merge. Merge will basically merge them in one single Boolean operation. Okay, perform intersection. Perfect. Now we have our master node, previous master node, our merge geometries, so the previous beams still continuous, but with this cut here. And then we have these 4 points that will be used later on. Now let me go back to the sub-geometry selection. So I switch this selection on, this selection off, so I can select the sub-geometries, and I'm going to select all these pieces that will be removed. Okay. Not this one, actually, this one is the okay, and the last 3 one here. We are going to remove them because we are going to use rigid links to take into account the panel zone effect of the corner. Once you have all of them selected, you can just press cancel. Okay. Now, as you can see here, we remove these lines, but in this case, we also removed the rigid diagram that was connected with those lines. Don't worry, because we are going to create it once again. Now, basically, we have all the beams and columns detached. Now we have the corner node, just one node here. Now, for the scissor model, we need to duplicate it. Okay, so let's select all the corner nodes. And we are just going to copy them upwards. Actually, they should be in the same position, okay? Because according to this formulation, let me show you, you will find it here. This is what we are going to do. Node A and node A prime should be coinciding. Now, just for the sake of simplicity, when we model them with a slight gap, and then when we are done with modeling, we move the nodes to the original position, okay? So we select all of them, and we move them of a small amount. Let me click move. Let's move it for a small amount. It's not important because after that, we will move them back to the original position, okay? Oh, actually, I made a mistake. I moved them. Actually, I have to copy them. So let me select them again. I need to copy them, not to move them. Okay, and let me press copy. Okay, perfect. Now they are copied. Okay, so now the next thing that we're going to do is to create a series of interactions to connect all these pieces. So let's go to interaction. The first interaction that we're going to do is the column to joint interaction. Okay, so we're going to connect all the columns. Let's take them as master nodes to the respective joint node. So the four master column nodes, right click, and we select all the original joint node. And right click. Okay, so now you have a series of one-to-one connections, as you can see here, one-to-one connection between the column and the joint. This will be the rigid part of the column. Then we do the same for the beams, but we will connect them to these other nodes. Okay, so once again, interaction, and we call it beam to joint. Okay, we select the joint as the master. It makes no difference, or it can be the beam. It makes no difference because we are going to use the penalty, otherwise there will be a difference. So let's select all the master nodes, then right click, and all the slave nodes that will be the beam ones. Okay, let's select them. And also these last two beam ends, right click, and then you have all these other connections, okay? So beams rigidly connected with the duplicated node of the joint. Finally, we need an interaction that connects the two joint nodes. Okay, so the original one and the duplicated one. And this interaction instead will be used to create the nonlinear spring. So joint. Okay, let's choose the original one as the master. Once again, it makes no difference here. Right click, and we choose the other ones as the slaves. And we are okay, right click. Perfect. So now we have all those interactions for the corner. As I told you before, doing this cut here, we removed accidentally the rigid diaphragm, so we're going to create it again. The interaction for rigid diaphragm. Okay, the master will be, of course, the master node, and the slave will be the original joint nodes. Okay, so this one, this one. So only the beams are attached to the previous ones. Okay, sorry, to the duplicated node. Right click, and we have this interaction. Perfect. Now, since this interaction has been removed, we need to go back to condition to reapply. Now that we have redrawn this one, we need to reapply the rigid diaphragm condition. So edit, we select this one. So now the rigid diaphragm is still applied to this new interaction. Now we need to assign something to all these new connections. Okay, so the first thing that we need to do is to create rigid links between using basically these and these connections here. So let's go to condition, and we are going to add joint rigid links. So we go on constraints, multi-point constraint, and we choose rigid link. We put it in 3D, and using the beam formulation. So both displacement and rotation are coupled. Now before pressing OK, we select all of these, like this one, just in one shot, and then all of the rigid links for the columns to joint, okay? So we just don't select this one that instead will not be rigid, but will be the nonlinear spring. And we press OK. So as you can see now, we have another boundary condition here. We define it, and we need to add it to the load step of the boundary condition. It is a multi-point constraint. We have just one of them, joint rigid links. So we increase this one by one, and we choose the rigid links. Okay. So now we have both the rigid diaphragm and the rigid links. Press OK. Now the last thing that we need to do is to create a nonlinear model for the joint. Okay, and then we are done. So let's go to physical properties. Pretty much like in shear, we need to create a uniaxial model for the two rotation in X and Y of the joint springs. So let's go to add. Now for simplicity, we give the same behavior in X and Y. So joint nonlinear material. This one in this case will be a pinching force. So uniaxial, some standard other uniaxial material. Pinching, where is the pinching for? Okay. Let me add some values for the joint. Okay, it is 165380. These are the stress points, so 248420, 261500, 112440, and then the deformation point 0.004, 0.00117, 0.0049, 0.0393. Okay, and then some other values here, 0.16, 0.23, minus 0.22, 0.85, 0, 0.12, 0.96, 0.38, 0, 0.34, 0, 0.96, and then all of them are 0, and the last one will be 100. Okay. Once again, let's do a small test. Okay, this is the behavior of our joint. Let's press OK. So here we have the joint nonlinear uniaxial material. Now the joint is actually a 6 degrees of freedom rigid link, actually a spring. So how do we simulate a string in OpenSys with zero length? So let's call this one joint zero length material. We go here, special purpose zero length material. 3D and 6 degrees of freedom, and we want to use all of them, so all of the 6 degrees of freedom. Basically, we will have this nonlinear behavior in the two rotation about the global x and y axis. For simplicity, we use the same nonlinear behavior in the two direction, and then all the others will be in continuity. So let's use the stiff material as before, as we did for the release. So stiff, stiff, and stiff also here. Perfect. Now we have the zero length joint material. Now we can select all the interaction for the joint, so these ones, as you can see. And we can drag and drop the joint zero length material. Perfect. Now, as a last step, we need to reselect them, joint, and we need to assign a finite element to them, because now they are not constraints, they are actually finite elements. So we need to drag and drop the zero length element we created before for the release, because actually it is the same element. Okay. So now we are done. Here we have a nonlinear behavior and a finite element, which is the zero length. Now, as I told you, I created this node slightly upwards, just for the sake of selection and visualization. It was not necessary, but it is easier to explain. Now that we are done, we can move these nodes downwards. Okay. So I'm going to select all these nodes here. Let me go back first to geometry. Okay. Let me select all these nodes. and I will move them to their original position from here to here. Okay. So now the zero length in there is still there, but it is not visible. Now we need to go here. We need to remesh the model because actually we changed it. We save it and we run the analysis. And this is the last thing that we added to our model. The selection set. Okay, since I removed this element, I need to go back to the selection set control node, and I need to add this node to selection set. So let me go back here, control node, add to selection set, because before I removed it. Okay, let me run the analysis. Oh, there is still this error. Let me see. Let me see what's going on here. Selection set number 1. Okay, let me remove it because probably I made a mistake. Let me go to geometry. Okay, let me remove the selection set. Let me remove it, rename it. Okay, delete. And now let me create it from the beginning. Probably I made a mistake and I didn't select it. So let me repeat this step, right click, and control node. Okay. Let's make sure that the vertex is selected. Okay. Back to the displacement control, edit, and okay, control node. Okay, we have done. Save it and run the analysis. Okay. Let's wait a few seconds. Now, as you can see, creating the beam column joints by hand is quite tedious. It takes a lot of time. It took almost 20 minutes. And that's why we are working on a simple procedure that lets you select only the vertices, and STKO will generate automatically the beam column joints. Now, it was not ready for today, so we will show you this new feature on the next webinar that will be on concentrated plasticity approach. So back to here. Let me reload. Let me see if I uncheck them all. Okay. Reload it. Okay. Now, as you can see, there are releases here. Okay. And let's first see the overall behavior. So let me select this one. And let me extract the displacement curve. Load displacement curve. So UX against the pseudo time step at the second stage. Next GF with joints. And let's see what's going on. Finish. Let me remove this one because I'm going to add it on top of this so we have a full comparison. Now we include also the behavior of the joint and see here how it changes. Now, of course, it changes based on the property that you give on the joint. Now we made the joint a little bit less stiff and with a lower strength. So as you can see here, you can keep on adding many features to describe a reinforced concrete structure. Okay. And then, of course, you can visualize the results on the joint that is here. The joint actually is a zero length, so it uses the material stress and material strain output. Now, as you can see here, you have two of them. Why? One of them, as you can see in this case, has 6 components, and is the one, as actually it has 5 components in this case, because it's the one for the release. And it is the one of the beam. Now, actually, we need to find the other result, which is the second one, which instead is for the joint, and it has 6 components. Okay. And then, of course, you can use the Gauss point plot to extract the data from this one. So let's see how this node is behaving. Now, this one is a Gauss point. So let's press next. Stage number 2. We want to plot a material strain number 2 versus material stress number 2, which is the one of the joints. And then we want the fifth component, which is the rotation about the global y-axis, so the rotation that we need actually. And also here, the fifth component. Next. And we call it joint stress strain curve. Okay, so this is what's going on in one of our joints. Okay, so as you can see, modeling the joints has its advantages. You can better describe the nonlinearity of your structure, but modeling them by hand, it takes a lot of time and it can be very error prone. Now, in this case, the structure was very small, but imagine to do the same on a real life structure. It will take time. So in the next webinar, we will show you how to do this automatically with a feature that we have in STKO. So for the moment, we are done with this webinar. So let's say we can have other 10 minutes of question if someone has questions. So please, if someone has questions, please. Is everything clear to everyone? Okay, I think so. Okay, so if it is fine for you, we can finish this webinar now. And okay, what if dynamic analysis is done instead of static? I mean, of course, you can do the dynamic analysis. Probably we can show it how to do dynamic analysis in the next webinar. We are going to do the next webinar. I don't remember the date, but you will see on the website, doing the same model, but with the lamp plasticity approach. Actually, an idea could be to do the dynamic analysis instead of the static one. So we can show you how to use uniform excitation and how to perform a transient analysis. So let's do this for the next webinar. But actually, the modeling procedure is the same. You just need to change the boundary conditions to include the uniform excitation, and you need to change the analysis command to include the transient analysis. Is there any other question? Can we do a separate webinar for wall micromodeling doing overall shear performance? Of course. Wall micromodeling, you mean in masonry or in reinforced concrete? Masonry, perfect. Yeah, we can do it on masonry because actually it's one of the topics we worked on, and I will show you in that webinar what is actually we will do the modeling with shells, okay? And I will show you that based on how you consider what shell you choose, so the thick one or the thin one of them will not be able to represent the out of plane shear failure, okay? This is a quite nice topic, so I will show you. The next webinar will be on reinforced concrete, lumped plasticity approach. The other one will be on solid structure interaction. So we can say the next one again can be this one on out of plane behavior of masonry. So thank you for the idea. Any other question? Okay, so if we don't have any other question, thank you to everyone. And you can see on the website, on our website, when will be the next webinar. So I hope to see you on the next webinar. Thank you all.